Welcome to our third video on the solution chemistry. This video topic is colligative properties. You see this one's labeled colligative properties 1. This video and the next will be on colligative properties. Just going to break that into a couple of shorter videos. Alright, we have 3 learning targets here in this lecture. First, we want to define and identify colligative properties. That's the first thing we'll get to. We want to determine the molality of electrolytes in solution. And then finally, we want to use a law called Raoult's law to determine the vapor pressure of a solution. A few resources here. Your text pages there are listed. And then a couple of videos. These are very good videos. I'll reference those here in a little bit. And then some practice problems if you want to access those. Alright, first of all, key ideas and definitions. First of all, we will just start with defining what a colligative property is. Colligative properties. A colligative property, it is a physical property of a solution that is affected by the number of solute particles but not the identity of the solute particles. So in other words, it doesn't matter what you dissolve in the solvent. These properties are only affected by how much you happen to dissolve. 4 basic colligative properties, 3 of which we will look at very closely in this class. The one we're going to look at in this lecture is vapor pressure. The 2 that we'll look at in our next video, boiling point and freezing point. And then there is a 4th that is referred to in the text that we're not going to deal with a whole lot in this class, and that is osmotic pressure. Dealing with osmosis. We might reference it a little bit, but we're not going to deal with that one nearly as much. Alright, another key idea or kind of a preliminary thing we need to get to before we look at some of the math behind this vapor pressure stuff is the idea of electrolytes in solution. So say we had an electrolyte. An electrolyte, one way to define it is something that will form charges whenever put into solution. So say, for example, we have sodium chloride. We know that's an ionic compound. When we dissolve that into water, we put it in water and it dissolves, we know that the ionic compound, which sodium chloride certainly is going to dissociate into its component ions. So if we look at sodium chloride, we're going to get 2 particles dissolved for every 1 particle that we place into it. Let's say we had 1 mole of sodium chloride that we dissolved into water. We are going to get 1 mole of sodium ions and 1 mole of chloride ions. In other words, 2 moles of particles. 2 moles total of particles. So if we were to say calculate the molality of a solution that was made by dissolving sodium chloride in water, the molality of the sodium chloride could be anything. Let's say it doesn't really matter what it is. Let's say the molality was 0.45 molal in HCl. We go to put that into water, and we're going to get twice the number of particles that we put into it. So the molality dealing with the particles would be 0.90 molal particles. And this is very important to us whenever we're dealing with colligative properties because we said it's determined, affected by the number of particles. Well, we get twice as many particles here as what we put in. We need to be able to account for that. We could do another example with something that gave you more than 2 particles. Say, for example, it was calcium chloride, CaCl2. That's going to split apart into a calcium ion and 2 chloride ions. And we get 3 particles for every one that we put in. So this is something we always need to consider. Now, not everything, as we know, is going to dissociate whenever it dissolves in a solute, in a solvent. For example, say we had sucrose. Sucrose is C12H22O11. This is just table sugar. If you take that and you dissolve it in water, it's not going to break apart into any ions. It's going to remain C12H22O11. Now it's going to be dissolved. It'll be aqueous. But however many particles you put in will be the number of particles in solution. So if it's a non-electrolyte, then I don't have to worry about determining how many particles I actually get, because it will always be the same. All right, the first colligative property. Let me kind of mark some of this stuff out here so we can separate this. Use a little more room than I thought I was going to. The first colligative property, and really the one we're going to focus on in this video, is vapor pressure. And what happens to vapor pressure whenever we dissolve a solute in a solvent? Recall from last year, we learned about this a little bit, that vapor pressure is something that we can measure and discuss for a liquid. Let's say I had a container of water, okay, container of water, and I sealed the container, I put some sort of lid on it, so nothing's going in, nothing's going out. Just based on random collisions between the water molecules, there will be, at times, certain water molecules that are able to escape into the gas phase. And thus there is some sort of pressure here that's being exerted by those water molecules that are now a vapor. So what this does is it actually gives you a measurable pressure. Now if we add a solute to this, say I add, doesn't matter, say I add some of this sodium chloride. Let's say I add some of the sodium chloride. And I add the same amount of water to the same temperature. Okay, but now I have some sodium chloride. The sodium chloride I'll just represent with some dots. I'll just put some random dots in here. Those are the particles of sodium or chlorine. Now those particles are going to take up some space. Simply going to take up space. Because they're taking up space, there will be less space for water molecules to escape up here into the vapor phase. So because there's less space, there will simply be fewer water molecules that have escaped into the gas phase. So very generally, we can say that adding a solute will lower the vapor pressure of a solvent. I'll just jot that down here. Adding a solute lowers the vapor pressure of a solvent. The more solute we add, the lower the vapor pressure should be, because there will be less and less and less space as we continue to add more of that solute. And as we saw up here, as far as our definition, it doesn't matter what the identity is of this solute. The only thing that matters is how many particles we have added to that solution. Alright, so let's jump down here and take a look at these example problems. The first one is more qualitative in nature, but we can talk some numbers. It says, which will lower the vapor pressure of a solvent more? Adding 1 mole of NaCl or 1 mole of, this would be glucose, C6H12O6. At first you might think, well, I'm adding 1 mole of each, so that's the same number of particles. And because we said colligative properties are based on number of particles, that they should be equal. They should lower the vapor pressure of the solvent, regardless of what the solvent is, the same amount, which is the same number of particles. However, if you consider what we just learned about the electrolytes, we can see here that sodium chloride, being an electrolyte, I'm just going to copy that same equation we had down earlier. If I take NaCl and I put it into water, I would get a mole of sodium ions, I get a mole of chloride ions. So this is 2 moles of particles. 2 moles of particles. Whereas the glucose, the C6H12O6, I put that into water. It's not an electrolyte. It's not going to dissociate. So it will still be C6H12O6, and I will still only have 1 mole of particles that I originally put in. So looking at it this way, we can see very clearly that the sodium chloride will lower the vapor pressure more. So the magic answer here is the NaCl. Because it being an electrolyte, it will give you more particles dissolved and thus will lower the vapor pressure more. All right. Let's see. Before we jump to the next example problem, a couple other things I do want to mention here. Jumping back up here, there's really nothing to write down here. This first video on Khan Academy, this does a real good job, I believe, of just explaining this vapor pressure idea. The diagrams might be a little more, I don't know, a little more descriptive of what I have here. So if you want, that was a little confusing to you, I'd check that out. The next video here, it's on YouTube, shows you a couple of examples using Raoult's law. Okay, and that's the quantitative relationship we're going to look at here. And I'm just going to jot down Raoult's law, and we'll explain what it is. Raoult's law says that the vapor pressure, so I'm just going to write capital P for that, of a solvent in a solution is equal to the mole fraction of that solvent times the vapor pressure of that solvent in the pure state. In other words, if nothing were dissolved in it. And this notation here looks like a superscript 0. It's read as naught, P naught, meaning the pure solvent. So to find the vapor pressure of the solvent, once we have something in it, we need to find its mole fraction. In other words, what fraction or percentage of the particles in the solution are actually the solvent, and multiply that by the pure vapor pressure of the solvent. All right, so let's take a look at the next example problem. There's actually only one more. This is a quantitative problem, so we have to use that Raoult's law. It says, suppose 651 grams of ethylene glycol, gives you the formula there, is dissolved in 1.50 kilograms of water. What is the vapor pressure of the water above the solution at 90 degrees Celsius? The vapor pressure of pure water at 90 degrees Celsius is 525.8 millimeters of mercury. All right, so just copying down Raoult's law here. Instead of putting solvent here, I'm going to put H2O because that is the solvent. So the vapor pressure of the water in the solution will equal the mole fraction of the water in the solution times the vapor pressure of pure water at that temperature. So the first thing we need to calculate, we need a mole fraction. We're going to need to convert these things to moles in here. Okay, so just doing some gram to mole calculations or kilogram to mole calculations, we have 1.50 kilograms of water. Converting that to grams, there's 1,000 grams in a kilogram, and then the molar mass of water is 18.02 grams per mole. Alright, this gives us a value of 83.2 moles of water. And then we need to do the same thing for the ethylene glycol as well. So we have 651 grams of that, of ethylene glycol. And the molar mass of the ethylene glycol is 62.07 grams. Ethylene glycol per mole. In case you were curious, ethylene glycol, that's antifreeze. So antifreeze is a solution of ethylene glycol. Alright, you do this, and this should give you a value of 10.5 moles of ethylene glycol. Now notice, ethylene glycol, it contains all nonmetals, so probably not going to dissociate. It's not an electrolyte, so I don't have to worry about if it's going to break up into any number of particles. That will be the number of particles that I get there from the 10.5 moles. Now I need to find the mole fraction of the water. Okay, this is something we normally don't do, find mole fractions of solvents, but in this case that's what I'm looking for. So the mole fraction of the water would equal the number of moles of water, 83.2 moles, divided by the total number of moles. So 83.2 moles plus the 10.5 moles, and I get a value of 0.888. So in other words, 88.8% of all the particles in this solution are water. So the vapor pressure should be 88.8% of what it would be if it were pure water. And that's exactly how Raoult's law works. Just using this law over here, I'm just going to take our mole fraction of water, just 0.888, multiply that by the vapor pressure of pure water, which we're told is 525.8 millimeters of mercury. And we get our value there. It looks like we get 3 sig figs. I get 467 millimeters of mercury. All right, one note, or kind of a side note, if you will, on Raoult's law. I'll just jot it down here. Raoult's, I'll spell it right, R-A-O-U-L-T apostrophe S. The law really only works for non-volatile solutes. In other words, solutes that aren't going to contribute to the vapor pressure. If I was dissolving something in water that was volatile, meaning it evaporated easily at room temperature, that's also going to contribute to the vapor pressure. There are ways to deal with that. We're really not going to deal with that in this class. It generally also only works for low concentrations. Now you might be thinking, well, how low is low enough? What do I need to know? For our purposes, we'll always just use Raoult's law. It maybe won't be the best approximation, but it will work for us. All right, one more problem here, a practice problem. So if you want to stop the video now, try this yourself, and then take a look at the solution. That might be a good way to go. All right, it says, what is the vapor pressure of water above a solution comprised of 3.4 grams of NaCl dissolved in 30 grams of water at 25 degrees Celsius? And again, it gives us the vapor pressure of the water. So very similar to the example problem we just did. We're going to need to calculate a mole fraction for the solvent, being water here. So I have 3.40 grams of NaCl, and I need to go grams to moles, and I have not yet worked this one out, so we're going to need to calculate the molar mass. Let's see, molar mass of NaCl is 58.44 grams NaCl per mole. NaCl, grams cancel. And you might think I'll just stop there. Well, remember though, sodium chloride is an electrolyte. We're going to get 2 moles of particles for every mole of NaCl. This has been the example we've used most often here. So I do need to have another conversion factor there. Alright, so this gives us, let's see, 3.4 divided by 58.44 times 2. That looks like we get 3 sig figs. I get 0.116 moles of particles. So now we need to do the same thing for the water, find how many moles there are. We have 30 grams of water. And molar mass is 18.02 grams per mole. So 30 divided by 18.02, I get 1.66 moles of water. Alright, so I still need to find a mole fraction. So the mole fraction of the water will be the number of moles of water, 1.66 moles, divided by the total number of moles, so 1.66 moles plus the 0.116 moles. Alright, so 1.66 divided by 1.66 plus 0.116, I get 0.935 for my mole fraction. So in other words, 93.5% of all the particles in the solution are water. So to find the vapor pressure of the water, I will take 0.935 times the vapor pressure of pure water at that temperature, 23.8 torr. And looks like I'm going to get 3 sig figs. 0.935 times 23.8. I get 22.3 22.3 torr. And there you have it.